So, can you hear us online?
Yes.
Okay, great. And welcome back. So, welcome back to the EA class. Just to summarize what we did last time, that we were moving, like still in the context of search problems, but moving from search algorithms and adversarial search to the knowledge representation part. It was an introduction in which we were going through both knowledge representation and uncertainty. So in this context, we were discussing logics as well, where we went, basically most of the time we spent on this logics timeline. And we were saying that in order to represent knowledge corresponding to things from the real world, we want to move from the very basic representation like logic, which is the classical logic, where we use binaries to represent things to a computer in order to program things. So we started, let me say, programming or representing the word as knowledge to a computer with the 0 and 1s. So it was a very basic representation where we represent things limited like day or night, black and white, things like that are binary, okay? Then we were moving and we said that the word is more complicated than this. And there is something called propositional logic. Propositional logic is coming from the word proposition. And proposition means some affirmation, some sentence, some truth that we are like announcing. For example, his name is Dallas, okay? This is a fact. We can denote that with P, for example, and P could be true or false. And we start discussing things like this, okay? Then we were moving to the first order logic, where like each time we are trying to approach the real world, this keep in mind. And the dimensions of the real world are that much high, n is, let's say, up to infinity. And each time we are adding things. Among these things was the linguistic variables. So sometimes I'm adding like quantifiers, sometimes I'm adding like different values. So I find myself in the first order logic, many values, things that I am analyzing, like the traffic light that could take value red, green, and blue, and so on. And also the epistemic logic, which introduces things like beliefs, like we are again more near to the real world. It introduced uncertainty, so I'm not sure if I'm still remember the name. And your name is, I believe that your name is Arshida. Yeah. So this is true. And then moving from these representations of the world, we are reaching to the fuzzy logics, and we were discussing this last time. Fuzzy logics, in briefly, is when we are almost like in the real world. And when we talk about the real world, it brings up to the table probabilities. Talk about probabilities, the sum of probabilities is always equal to 1. If, for example, we are discussing before, it's the same example, cold or hot, means the probability of being cold, if I say yes, it's cold, it's 1, and for hot, it's 0, and vice versa, okay? In the case of fuzzy logics, we don't have this example. We can say that it's not strictly like 100% or with the probability of 1 hot or probability of 1 of 0 cold, sorry. We say that I'm feeling cold, okay? It's 70%, like same percentage last time, cold. Still 30% hot, means the sum of probabilities is equal to 1 or 100%, okay? So here we are approaching to the reality, and still we are not like completely modeling or representing the reality for sure. Is that clear for everyone? Just a brief summary to understand the context. Okay, so we started with the classical logic is clear for everyone, I believe. P and Q and true or false. So we started really with propositional logic last time. This is what we will do this class. Next, we are going to see the example of first order logic. As I was mentioning, in this AI class, it's my role to introduce like such knowledge, but it may be taken in different course, okay? But still, we were like discussing that we can explore together fuzzy logics, because I love when my students like are more advanced, they know more things. So in this context, I still remember that Zoya is saying I would like present fuzzy logics, and you expect this. Yeah, Zoya's here.
Yep.
Okay, great.
Sorry, I had trouble getting in the meeting.
Yeah, I'm not forgetting to send you an email. So we are planning that to be in the review session, just like some knowledge, and then we will have the review for the exam. Now, if I'm talking about the exam, based on the syllabus, so it was like planified for next week. However, still we are not like going through the Bayesian networks and the like Bayesian networks over time. So I think that we finish this first part of the basics of machine learning, AI. And once done with that, like the first week of October, we go through our review session, the presentation of the fuzzy logics, and we have our exam. So I just want to take your opinion. If you agree that the exam won't be next week, and it will be the first week of October. No problem.
Yeah, sounds
Okay.
good. I like the idea of pushing it forward.
Okay, great. So because we need to work on the presentation as well. Yeah, I'm going to announce that in the announcements. This is something else. I'm not also forgetting Jeremy. So we are going also to present like programming attempt for solving the min-max algorithm as well, if we will be having time. Otherwise, we'll be recording that and share with you guys. Something else is that some of you told me that there is a problem in accessing the records of the class, and this is why I'm creating a YouTube channel. Like it's only like those having the link and access to that, like videos, where you can find all the videos of our lectures. Any questions? Okay, so let's come back. Quickly, we are going to start with the propositional logic, coming in the context of agent, which is this time not going to be a simple entity that perceives and reacts. It's going to have some knowledge-based like representation. And this agent has like acting and reacting, having like queries and giving conclusions with the like environment. So these such like decisions or inferences or conclusions are based on both the knowledge base and the inference engine. Okay, it's going to take such decisions that we are going to output to the real world, for example. Okay, so this is the context, and we already started with the basics of propositional logic. Here we will quickly go through this for those who were like missing last time class. This represents, like, as I was mentioning, my name is X, your name is Y. So my name is X is going to be represented with P, your name is Y is going to be presented with Q. And so these are proposition symbols, okay? And we can not move from atomic representation, means I have only one sentence or one proposition, towards like describing a more complex problems. And how I am going to put all this together is thanks to connectives. This table represents the existing like connectives for this logic, and every logic, to keep in mind, comes with different connectives, okay? So in this case, we have the negation. So my name could be X, which represents P, fact. The negation of that, my name is not X anymore, okay? The conjunction, I have this sample, it's saying like and, P and Q. It means at the same time these things are happening, like simultaneous things are happening, for example. This junction is saying whether I have P or Q, one of them. And the implications, it means P implies Q, means the reason that is taking me to Q is P, okay? And the biconditional, it's like in both sense, in both like directions, implication, which means P implies Q and Q implies P, okay? It's biconditional. So keeping this in mind, we are going to move forward. We already had this example of a quiz. So I invite those who didn't take as well. And we are trying to guess, for example, if I have like P and Q, how many possible like rows can I have in this table? 4, okay? So whether P is false, Q is false. And in this case, the opposite of P, the not P is going to be not false is true, okay? P and Q, false and false, will give false. P or Q, one of them is false, it's enough to have the output as false, so it's false. P implies Q, false implies false, that's true. And the B, like conditional, is also given true. So we have the different like combinations and the different results. Next, we had this quiz. So the correction of the quiz is that if we have false for P and false for Q, both are false, P or Q gives, now I need to hear, false, okay? P or Q, which is already false, if I will add that to and not Q, so not Q in this case is not false, means true, true and that previous false, going to give false. And then I have all this, which is now false. I'm evaluating this, the P or Q and the not Q. Is it going to imply P or not? Now, P, which is false, P in false. So is false implies false? Yep, that's true. Okay, this is the same logic that we are applying here to get these results. So for the last one, let's retake this one. So if I have true and true, okay, the OR is giving true. If I have like true and not true means false, means true and false is giving false. Now I have that false. Is it going to imply true?
False.
To make sure.
True. False implies true.
So we have here this entity which is given false, okay, and false implies P, which is true. False implies true. So let's check here. If I have the implies, P implies Q, so false implies true is true. False implies false is the only case where I have the final result as false. True.
Not convinced, because if we have true, how does it implies false?
No, we are not saying that true is implying false. That true is the whole like.
True implies.
Okay, if I have something false,
yeah,
is it going to imply false?
Yeah.
Yeah. If I have something true, is it going to imply true?
Yeah.
Yeah. So this is clear. False, false implies true. True, true implies true. Okay. Now, something is false. I can start from false as like assumption. Your name is Ayub for Farah. It can happen that this is something is false. It's implying something true. It can by luck, I'm coming, you are Ayub, and it's happening that it's Ayub. And then the only case that cannot give true, if I start from something I'm sure it's true, it can lead to true, not false. Okay? So this table was the fact. Now we are dealing with this table. Based on this table, you always evaluate. Okay? So after that, we were moving to the logical equivalence.
Can we do something real quick for 1 second?
Yeah.
Because I think if we go back to your previous slide, there's a true implies false, one more to 76.
This one. True, false implies false. Yeah.
Yep, but that I think is different on 76. If you go 2 more slides down.
Which one?
Yep, so if we go to
It's false. Implies true.
TF, so the third from the bottom, and then all the way over to the right.
This last line you're discussing,
Nope,
Jeremy?
up one.
Okay.
So P is true, Q is false, and then the first one's true, and then the next one's false, and then it looks like the true group from the last one is implying, yep, it's P at the end. Never mind, my mistake.
Okay. So
Sorry.
who's still not convinced? Yeah, I like this. I like that you understand things right now. You can try to focus a little bit. You can even speak in a loud voice so we can understand together.
Could we go through some more examples?
Yep, we are going to have plenty of examples. Okay. But this table is the fact now. Now, for each example, we are going to come to this table. So if I having this P is false, the not P is true. This is the final rule. This is the final table, okay? And each time we're going to be based on this table.
Sorry to interrupt. I think there's a student in the waiting room for this class.
Oh, thank you for letting me know.
Yeah.
Okay.
Where do you
Thanks.
see that?
I'm hoping it's this class, or otherwise I just got spam mail.
Okay. So now let's move to the second part. So this also, I think we came through this one last time. So what we have now, there are like logical equivalence where we have each time some like representation of this knowledge and it's equivalent. Means if I write this or this is the same thing, this or this also is the same thing, okay? So if I would be having P and Q, it's the same thing that I have Q and P. So we have the commutativity of the AND. Also, it's the same for the OR. If I switch the order, it's the same thing. It don't matter. Then I have the associativity of the AND. It's same like in maths. If I have P and Q and I have my parentheses here, okay? And R, all this and R, I will be like having P and R. P, I'm keeping out, and I will change the position of the parentheses. I put this block together or this block together, no worries, because I still have and, okay? I can associate different blocks together if unless and until I'm having the same like symbol, which is and, okay? It's also the same for the or. If I have my parentheses here, I can place it also here, no worries, okay? Because I have or, just need to check. Then the double negation here, it implies like I'm going to eliminate that. So not P is the opposite of P. So not P gives P. We come back to the same point. So this is the double negation elimination. And then please keep this in mind because we'll see it later and I'm sure that we may come back to this slide. So if you have notes, try to take notes of this. Maybe you get examples. So P implies Q here. If I have P implies Q, it's the same that not Q can take me to the not P. So if I am going to switch the direction of the implies, I'm just going to add the negation. It can take me to the opposite like sense, which is known as contraposition. Then the application elimination. Now this also take note that most of the time if I have application, for one reason or another, we'll see later, I sometimes don't want to see this application. I want to eliminate the application, and I will explain why. If I see P implies Q and I want to remove this implication, I will make it none P or Q. It's like this rule is implication elimination. I can also eliminate the preconditional by, for example, if I have P and in like both like directions, Q, which is P can take me to Q, Q can take me back to P. Here is same, like P from Q, I can write it this way. Q that can take me to P, I can also write it like this, and I will have an and because I will go in the first like direction and then I will go in the second direction. Is that clear, please? Okay, then we have the De Morgan rule, and that applies for both like and or. So here, if I have my parenthesis here and a not that is applying in the whole like block, let me call it. If I want to like remove my parenthesis, so how would it be? What will happen is that if I have an and, I will make my not inside and I will get the opposite, okay? And the same, if I have not and I have or, then if I have not for both elements, I will be having and. I will do the opposite of what symbol I have. Is that clear? Next, we have this recurrency and of the and over the or, and the same of the or over the and. So here we can, this was the example. P and I have it together, Q or R, so I can make it P and Q, or again P and R, okay? And the same for the O. So is that clear? We may be using this set of tools, especially those that eliminating the like implication or the preconditional, okay? So we had this quiz. Yep. We went through this quiz. Yep. Okay, now
Not this one.
we have this one. Try to connect to your canvas and let me just share it with you. Yep. So you can find, we start quiz 2, proving chain rule. Okay, instead of giving you like the rule, I want to guess it. Because once you will guess it, you will learn it forever. And like this, it's done, it's given.
I don't have the quiz on.
I'm done right now. Yeah, just refresh and you will get it. So it's right here online.
Okay, I can see it now.
He unmuted, but I didn't hear him.
Yeah, I'm here. Sorry. Thank
There
you.
we go. Yep.
Okay, great. Welcome. And for the Zoom link, it's supposed to be in your calendar, right?
Yeah, I did actually find it in my calendar. Sorry, I joined it early and
okay,
I
okay.
thought I had the
No
wrong
worries.
meeting. So now I got the right.
No worries. try to think, okay? Try to think and do it. In the exam, it will be allowed to use whatever you want to use. But now I just want you to learn. This is why you just need to think. Done? Yes. Everyone? Who's still no?
Yep, I'm done.
Okay, okay. Just.
So I'm a little confused about what we're supposed to do for the proof of chain rule, the second quiz.
I think we
So not
move
this
all
one.
together for better. So it's done?
Oh, I was doing the second one.
Oh,
Oh.
no worries. Okay, so I have P implies Q. And this Q, where I am right now, will take me to R, implies R. So does P implies R correct? It's true or false?
True.
True.
Good job. So it's true. Now the next one. That's the next one, the proof of chain rule, not more.
So this one I was also still thinking it's true. Like if P is true, that makes Q true, which also makes R true.
We have P implies Q is true and Q implies R is true. This is the same example we were just now. But the thing that P, Q, and R can get like different like values. Just try to guess. Based on the facts you will have on each, like treat it like row by row, okay? First you answer the first and second answer, based on that, then the rest. So here, if I don't have anything in the Q and R, like, means there is no information available about that. Only from the given information, I need to get my conclusion.
I don't think it's possible. How about that?
So like one of them could be true and then they're all true, and then the other one, P would be false, and then Q and R would also be false, but P would still imply R, and that would be true, but P, Q, and R would be false, I think.
In all cases, just give it a try. Everyone is working like separately, and then we are going to discuss together.
But like I think we would need a starting place. We'd have to know whether P is either true or false to be able to fill out the rest, I think.
P could be false or true. Let's take the first case for answer 1.
In that case, I think Q and R would be false. But P could still imply Q, and Q could still imply R, and P could still imply R. Those would still be true, but P, Q, and R would be false.
So let's like find the second answer if everyone is done. I know that P implies Q is true, okay? And that Q implies R is true. So P is Q, P implies R is true. Okay, then the next one. If I taken one time it's false, then the next time it would be true.
True.
So if my P is true, P implies Q is true, Q implies R is true, P implies R is
True.
It's very simple, but I just want to do it yourself. Don't complicate things. Okay? So now let's move to the next quiz, which is taking like an example. Let's consider it could be a real example. There is an alarm. The alarm is there. There are two like reasons, let's say. The first one is burglary, and the second one is earthquake. Because of that, like there is an alarm. There is an alarm. Maybe Mary could be calling, or John also can call. So given these 5 Boolean proposition samples, try to fill, and like this logic, if I have B for each time, for example, I have like proposition, I'm going just to denote it by the first letter, okay? A for alarm, like this, okay? So if I have B or E, this will take me to implies A. And if I have A, this will imply M or J. How is it? Keep in mind it's very simple. Done? Correct?
The exclamation mark is not correct.
Because it means I don't know. I don't have information about that.
Yeah, if we have E or B, it will be alarm. So
If something
suppose-
I don't have like any knowledge, if that is like true or false, then I will be putting that mark. Means it's unknown, let's say. I don't know. I don't have enough information to decide whether it's true or false. Online, it's done.
So I do have one question. Would it be is it supposed to be A implies M and J or A implies M or J?
Which one?
So like in the quiz it's reading as A implies M and J, and I was thinking it should be based on the picture A implies M or J.
Okay, then here we will keep it and. The same as in the table.
Okay, makes sense.
But it's a very good like one. It's done. Okay, so are you done? Correct answers? Okay, so we have the first one, which is true. B or E implies A. Then I have A implies N and J. So B, if I have knowledge that B is true in this case, okay? What E is going to have as a result? It could be true, it could be false, so we don't have enough knowledge, so we don't know. Okay, then for A, true. Then M, true, and we don't know. Is that okay? Okay,
That
just
makes
to
sense.
let you know. Zoya is all right?
Yeah, I think I get it now. Thank you.
Okay, so here, just in the exam, I'm not going to answer any questions because I'm giving the exam, I'm giving like full access to everything. The only thing is, don't ask me if I'm wrong or not. If I'm keeping it like that wrong, I want to solve it as it is, okay? Just, it's a practice for that. So now let's move to a more, let me say, illustrating example. I don't know if you guys heard about this or not before.
Yeah, it's in
Okay.
the book.
Great. So this is the Rumpus word, which is given or represented by a 4x4 grid, resulting in having how many elements, or let's call them rooms? 16. Okay? So let's consider the whole thing as a cave. Okay? And in this cave, imagine having 16 rooms. And in each rooms, we are going to have some things. Okay, we'll discuss that. But in the main gate or the entrance of this like room or cave, first room is going to have, let's call it like the coordinates of the first element, which is, what is our first element in this case? What is our first element? Yeah, the starting point. That guy, what is that? this is someone or someone?
Like
So-
like an
Who is this?
agent.
Exactly. We're doing AI, we're discussing about agents. Now we are introducing the knowledge base to this agent. So this could be the agent, which is not the typical agent. The agent with knowledge base in the context of propositional logic. Okay? So this agent is stuck at this point and has some problem. The problem is like to have like successfully reach to this room where we can find the gold. It's like a game, okay? And some rooms are empty. Some rooms are having what we call breeze. It's like some fresh air coming from pit. Pit is somewhere where this agent could fall. And if he's falling, then game over. He cannot come out. He's dead. Or this like agent can come, unfortunately, to this room where there is the wampus, which is a monster. So how can this agent guess? I would say guess, because we know that the agent perceives its environment. Perceives environments thanks to who is saying something? Extra points. So I will take notes at the end. I'm not forgetting Jeremy, Farah, and Dallas. I'm going to add a column in the grading book for extra points. So we are going to guess thanks to sensors. If I'm going, how can I guess if there is a monster? If I will be smelling like a very bad smell known as stench, then there is a monster. I find it in the, where I will find that? In the rooms or squares that are adjacent to the wampus. They are smelly. Squares that are adjacent to the pit, they are breezy. And in the start, we start with our agent at the point with coordinates 1, 1. It's this point, okay? This room. It's having coordinates 1, 1. And we will be navigating, so we are going to deal from now, like say, for example, this is the I-axis and this is the G-axis. And based on that, we can guess which coordinates this agent is having at each position, okay? So just what we have as additional knowledge, this first like entrance point is the same as the exit. So it's not about reaching to the goal, successfully coming back to the same point from where the agent has started, okay? So after that, the agent is going to reach to the glitter, which is at the same like room where we have the gold, like breeze and stench, if and only if gold is in the same square. So it's at that same square where almost everything which is not dangerous is there. So it's clear that these like rooms are not dangerous. Only where there are pits or wampus, it's dangerous. And what is the agent going to do? He's going to walk into a wall and bump. He can or he have the possibility to shot directly at wampus here, and what will happen there? No matter how far, it's going to scream and die. The wampus or the master is going to scream in that case and die. Then, and the only arrow that will be used up in this case, we can, in this environment also we can find the grab or release, where the gold means taking the gold. If we are at that same square, we are reaching to that gold, okay? So this defines the environment. The performance like of this agent, because the agent, if he's doing something, he's moving to the right direction, he's getting a word at least. If not, means there is a penalty. So there is, if he's reaching to the goal, there is a 1,000 award. In case that he's there at the square where the wampus is, so it's death. This is the first case. The second one, in case he's at a bit like row. Next, each step is going to deduct -1 from his score, and in case he want to use the arrow, that is going to result deducting -10 points. Okay, so now we're defining the performance measures, the environment. The actuators are what? Actions that this agent can take, can move right, left, he can go forward, he can grab, release, or short. So in the initial position, once the agent is here, what possible actions, let's say, that he can take? What are his possible actuators in this case? Only 2 are possible. Okay, if I want to go this side,
Isn't there a third? You can shoot his arrow.
like you want to go this direction?
Well, you can shoot it
No,
out.
no. At this case, no. But we are taking the very basic one. This is, I'm trying to explain, is the most complex. Then we are going to simplify things to have it in less steps and so on, just to try to follow the logic. For now, to make it simple, we go right or up. So in this way, you cannot go like down. I also cannot go because this is a wall. Okay. What will happen now? After defining this Wampus word, we are going to first go through the characteristics of this environment or this world. This is partially observable. We cannot see it all because at this position 1-1, he can see the room that is just next from the right side or upper side. Okay. Then it's deterministic because we know that the outcomes, they are specified. We know them exactly. It's sequential because we are having at a given level set of actions like sequences that is taken as or like moving. The static Wampus and pits are not going to move. Means otherwise the opposite of static is dynamic. And this may be in a more advanced level or versions of this game where the Wampus each, for example, like time slots going to move to a different room. We are not considering that, so it's static. And then it's discrete because we have the exact finite like grid in this case, and it's a single agent, means the Wampus is essentially a natural feature. We only have one agent. Okay, so what we have now, we have the main challenges that the agent may face. First of all, that it doesn't know the configuration. That also how to reason about this configuration is a challenge. And the knowledge involves as new percepts arrive and actions are taken. Because the environment is not fully observable, so each time he can decide, because each time he can only decide based on the information that are in the adjacent rooms. Okay, so he don't have the full access to what is, for example, in the next room. I don't know what's here. I don't know what's here. I don't know what's here. Is that clear? Okay. Now, is this clear for everyone? The concept is clear? Online? Okay, great. Now, let's try to explore this Wampus word. So, if he is now at the starting point, that point with the coordinates 1-1, and he's not dead, he's there, it means that this is okay for him. And what he can guess, what moves he can take. For him, yep, for him it's okay to go up or this way, right? If he's going up, let's suppose at this point, the sensors are detecting breeze. So there is some breeze. In this case, what will come, what is the conclusion? What is going to indicate if there is a breeze? If there is a breeze, it indicates that whether in the next 2 adjacent rooms, there is a pit, means there is danger. So in this case, is the agent safe to move there? No. What can the agent do at this position?
Go back.
You can go,
Go
backwards.
back? Good job. He can go back because he knows that at the point or the position with coordinates 1, 1, there is nothing. Okay. Once he go back, he can explore the other remaining empty room, because in case we are considering that he's having 2 only like rooms to explore, if this one is done explored and I cannot move forward, I'm coming back, what I have to explore? I will not stay in this infinite loop exploring the same thing, so I will move to the other one. Is that clear? Now moving to the other one, let's suppose that sensors are detecting some smell. He's smelling something. Smelling something indicates what? That there is a wampus, whether in this room or in this room. Now, he's having knowledge about this path he's taking and what is happening here, or it's possible to be. We are not sure if the pit is here or here. At this point, we know that there could be wampus here or here. But given this room now, what extra knowledge we have? We have 2 possibilities. Whether they could be pit or also it could be wampus. In this case, what you suggest to the agent?
Go up.
Either
Let me
move
see.
up or shoot
So,
to the right.
is it possible to have it both, like
No.
pit and wampus? No. So it's okay to go up. And if here it's okay to go up, means there is no problem here. Means here I must be having pit. It's confirmed now. And here is confirmed. If this here it's okay and there is no wampus, then the wampus must be here with a probability of 100% sure. Okay? Is that clear, everyone? Please, online.
Yep.
Good. Okay. Now we are at this point. What can happen? We will
should
not
probably
go
go
to the compass. We are going to go up. If up, then here it's okay, and there is okay. We are starting to explore the wampus world, and let's suppose that the glitter sensors are there, the glitter, and we're having the smell, the breeze, and everything is there. So it's almost like with this concept, we can explore this game. So each time we are having what? Assumptions, and we are not sure if that's true or not. This is called inference, and each time the agent is not sure. He don't know if like that inference is true or false, and each time what he's trying to do, given a knowledge base, he's trying to check the inference, is it that means true or not? So how to do that? We started doing already,
Explore more.
exploring that. And this could happen thanks to propositional theorem proving. This is a very basic example. Now we are, is there any and or whatever we're seeing so far? No, still we are just exploring the game. Now, once like we have that basic, we are understanding the logics, we are going to think of it given the knowledge base and the inference engine. So let's denote together, let's agree that P of IG is true if there is a pit in that position IG. Okay, let's like now say that this is, for example, I and this is G. You can reverse the order, just you are studying this example. Okay, so we have, if I will ask you now about this point. What is this?
It's unexplored.
Suppose, just an example. This is P. Can you give me the exact coordinates of this P? Hmm? 1, 2, 3. Okay. So it's 3, comma 3. Okay. So if there is a pit here, I will denote it with P33 at the position 3, 3. If there is no pit, there could be. What could be there? Breeze. So whether I have my P at that point of coordinates IG to denote that there is a pit there, so that's true, or to denote that there is a breeze there, and that's true. Okay, it depends. Now let's consider this grid, and we are going to define our knowledge base. Our knowledge base is going to introduce five rules. So we have R1 and R2 and until R5. Okay? Now, what are these rules? Let's define the rules. We were just talking. It was just abstraction. Now we are going to represent that. So we know that we have P and B and the positions each time. So let's suppose first time, where is your agent?
1, 1.
So is there a pit there? How to say that no pit at the position 1, 1?
False.
Huh?
I don't understand false.
Negative P.
Negative P. No. Negative P where? 3, 3? 1, 1. You need to define exactly. We have the IG. We need to respect that. So it's like a template. You need to follow. So in the P11, that is more important because when I see P, it means it's a pit. I'm not specifying the location. Okay, it's the very first rule. Okay, of coordinates 1, 1. There is no pit there. The second rule, which seems easy to guess, the rule 2. Online, try to be active.
Well, it seems like there could be a lot of them depending on, I guess I don't,
Oh, I have an idea.
like the order
we have-
shouldn't matter.
I'm giving you a guide that the agent is at the position 1, 1. From that, we said that at this position, there is no P11. What could be the other rules given what I'm saying?
Gotcha.
There's also no B.
P equivalent to B. What that.
We're not reaching that level. Just very simple. He's there. There is no pit.
That worked.
Also, there must be no breeze. He's not dead. So I think you are guessing first. So you are going to write names at the end. So we have extra points. Ayub has extra points for today. And the third one, if, for example, in the room, which is like, if he's going to move up, there is a breeze. So that denotes B 2, 1. We're having the coordinates 2, 1. And the other rule now is
P2.
B 1, 1. It means what? If there is breeze at the position 1, 1,
It means there must be a pit
if
at
and
either.
only if there is 2 ways. You are right.
There is pit.
There is pit whether at the position adjacent ones 1, 2 or 2, 1. Right, Zoya?
Yeah.
Okay. So now, what is the other rule? The fifth one?
Breeze in the adjacent.
Yeah. Breeze 1, 1. Now we're having the breeze 2, 1, which is already mentioned there. If we have breeze at the position 2, 1, that could indicate what?
There must be
A pit where?
the
In
three
whether up or down or
right.
the right side, let's suppose the right side. Okay, is that clear? So it's P11 or P21 or P31, one of them. Now, doing all this, where we were coming? Which, like,
So the logical.
target inference? We were guessing right now, but only using our language. Now, if I have all this knowledge, this will take me to the target inference that at the position 1, 2, there is no pit. And this is why he was moving there already. Is that clear? So this is, we are modeling or representing this problem given the propositional logic, okay? Anyone is having questions? Try to ask.
In the last statement,
Target
after
inference.
this appearance, it's not P1, it's given for us or based
No,
on the knowledge base?
It's based on these rules. We are getting this one.
So the conjunction between R1, R2, R3.
It's not really conjunction, but the logic behind.
Oh,
Yeah. So let's, if you want to, anyone is getting how we are reaching to the target inference here?
because it could be another.
No, we were already getting this now. Before we are already getting this. But after modeling now with these rules, we're getting the same thing. Now, forget the logic we had. Try to think with this like samples that we are introducing right now. Online, anyone is understanding the target inference, why it's not P12?
Yeah, that makes sense. Like it was proved from the other rules.
Which rule exactly? If you can explain, Zoya.
So for instance, let me move back to the slide so I can see all the rules. So we see that in 2.1,
Which rule?
For rule 2, we see there's no breeze. So that's an important rule. And then we also see that like if there's no breeze, then there's no pit. And then that would be rule. Okay, so from rule 4, we see like if there was a breeze, then there would have been a pit in either 1.2 or 2.1. But because there wasn't a breeze, we know there's not a pit in either 1.2 or 2.1.
You're right, you're having extra points. But I won't give it until everyone is understanding. Anyone is not understanding?
Sorry, I'm terrible at explaining this.
Yeah, you're explaining well, but I think they want to see it rather than, right? I illustrated. It's clear? So what she's doing, Zoya, she's starting like rule by rule. The first one, she's just trying to illustrate in this space here. So the first one is that we already know that there is no pit here, not P11. And also we have not B11. If I am going to move, I have already this my B to 1. How can I get this one? It's based on these two rules. In each case, I am going to call my knowledge about the previous rules. And this is what we already did. So is there B11 here? It's not. And is there here like P11? It's not. So given this combination, what we are going to, we have here already P1, 2, 2, 1, 1, 1, 2, 2, 3, 1. So what is going to remain if we keep the same logic until the end? We will only having the not P1, 2. Is that clear? Okay, that's great. Okay, Ayub, Arshida, and Zoya. Extra points. Okay. How are we proving this? So now first thing is that we are thinking this much, we are still even thinking of taking the first step. You can see how like it's not an easy process. So just to come at the end, if we are going to explore only this 4x4 grid or 16 rooms, it's going to take too much time and space complexity. So for n samples, we have like O of the complexity is in the order of O to like power n time complexity, and O of n is the space complexity. We're going to explore all the rooms n, and each time it's going to be 2 power n. And in this case of 46 distinct like propositions, we talk about 155 sentences if we are writing this in the like propositions like way. One way to prove this is through enumeration. And when I say enumeration, it's kind you're taking a pen and paper and you are going to enumerate. What are you going to enumerate in this case? You are going to see what you have. You have, for example, for B, based on the representation there, it could be at position 1, 1 or 2, 1. This is the possible, like, based on that rules we are defining. We have, as compared to P, the pit, position 1, 1, 1, 2, 2, 1, 2, 2, and 3, 1. Just to make you remember, this side we are putting like the symbols, and in the other side we are putting the rules, and from all this we are entering the knowledge base. So just this is from where we are getting this like B and P values, okay? The different one existing here, and then we put the different rules, and then we start evaluating our knowledge base. We evaluate that by giving the different possible like values that could be taken, true, false, false, positive, like every possible like combination of possible values, okay? So given that, for example, we find only true values when we have that given setting, for example, okay? So it shows the complexity in terms of both time and space. Another way to prove that is to use the propositional theorem. Means I'm not going to enumerate all possible ways, including the false one, which are going to be useless for me. So I am going to start with applying the fourth rule. I have B11 like B conditional taken to P12 or P21. From here, I can be like removing that biconditional arouse, if you still remember, to get what? A biconditional B or C is going to give A implies B or C and the opposite direction. Is that clear?
Yeah.
So from that, what can I do at this level? Still, I can reduce it more. So what are we doing at this point? We are considering P12 and P21, which is implying B11. And after that, we are going to apply the contraposition. So we need the negation here because we don't have B11 in our graph. We're having first, we're still at the first position, not B11. We need to have the not because we are coming to like the B and we need to have not B. So applying that not to B11, it means that we are applying the not to P12 or P21. Applying negation to this will result in what? Not?
Will just be not P, right?
Yeah, not P12 and not P21.
Not P21.
Okay. Then this is what we are reaching. And if I am removing the parentheses, I have a not outside. Removing the parentheses will cost me the opposite of the symbol inside. If I have an and, it will be an or. If I have an or, it will be an and. Okay? So I'm coming to this point, which is not P12 and not P21, which is not P12. So I'm coming to the same point with a different way, which is taking to the same point. So we're having the first reasoning that we had together, propositional like description of this problem. We tried to go through enumerating all the possible like scenarios and guessing where it's true, it's taking us to not P12, or we are starting from a given rule, like Zoya was explaining, and based on this like reasoning, we are coming to the point or decision that next move is going to be not, there is no pit in 1, 2 like position. Clear?
So that's a dumb question. Can you
Yeah.
start with any rule, or do you try to
No,
pick
sure.
one that has the most terms?
Okay, here to keep your extra points, I will ask you the same question. What you did you start with any rule or you are selecting a given rule?
I selected the one that had the relevant terms to like start with.
Yeah, this is what we did. Because let's suppose that you are starting with rule 1. What rule 1 says? This is very simple
There's
and it's
not a
useless
bit.
even to start with this. Okay?
Okay, that would help.
So we keep your extra points.
I get it. Okay.
Okay.
I have a question.
So, yep.
If we have not P1, 2, and not P2, 1, why are we choosing not P1, 2?
Because based on the rule here, we have already there is not P12 in the first position. He is at that not P12.
So we'll have not P2, 1.
No, 1, 2.
Okay.
Okay. So, is that clear, please?
Yep.
Good. What are we doing? You need to ask yourself this from time to time. We are at the AI class. We started with search algorithm. We are finding ourselves at propositional logic. Each time we need to do mapping where we are based on the context. So we are always in the still chapter search problems. And we were saying that when we have a search problem, we have initial state. From my initial state, I can take actions that can take me to different other states, which is going to give me the whole like transition model, or I'm going to be moving in a given space. And then why I'm moving? For reaching to a given point, which is the goal test. Each time I'm at a different point, I'm evaluating if this the goal or not, and testing if that is the goal or not. And once there, reaching, I check how much I've spent. What is my path cost at this level? Okay, so this is where we are. And what we are dealing with now is the theorem proving. Still, at least we have the agent. It's clear that it's the same agent, the entity that is perceiving its environment and acting like accordingly. But here, we need to do some mapping between like this, like search problems, and the theorem proving that we are discussing right now. So the initial state, in this case, corresponds to the starting knowledge base, which is there, the position of the, it's not the simple agent, the knowledge base agent, okay? So what actions this agent is taking, I'm still calling it action, but really I'm wrong, it's not actions. It is what inference rules that are going to be followed by our intelligent agent. Okay, the transition model is corresponding to the new knowledge base after inference. Our goal test, which is our purpose, is to check the statement we are trying to prove. For example, we are trying to reach to the goal. And each time, if we are at some point, is this the goal or not? If means I'm going to pick or not. You always keep that in mind. The path cost function, if we are evaluating the complexity of the problem, and we said it's at the order of n. If I'm having a grid of 16 elements, so complexity is 16. So it's the number of steps in proof. Each time it's going to cost me 1. Okay? What we are going to discuss now, is that clear, please? So you are mapping the context, still we are there. No one is lost.
Yeah.
Online, no
makes
one is lost.
Yeah.
Okay, great. So the inference path now is derived by hand with human intelligence. It means what? I will become that professor reading the slides right now. And you will explain. Extra points. What is the inference path? The reasoning using the propositional logic that we are now executing. This is now done how? Is it the machine executing that? Is it your smart agent doing something? Who is smart, you or your agent until now? It's you. It's me who is talking now 1 hour moving here, moving not that, this one. You understand? So until now, we are only relying on the human intelligence and what we are doing. It's not HR, it's AI. So how to switch? How can an intelligent agent perform such inference in general, which is introduced by human intelligence?
Set of rules,
Mm-hmm.
programs,
Yes.
instructions.
Yep. And there is something which is called the proof by resolution. This is the right answer. Proof by resolution. Someone to read, please.
I got you.
You will read it to get it.
Want to read it?
You will read it, so I'm sure that you will forever memorize it.
Okay, let's go. Proof by resolution is a powerful and widely used method in propositional logic for theorem proving. It works by trying to derive a contradiction from a given set of clauses and a negation of the statement we want to prove. If a contradiction is found, it confirms that the original statement must be true. This method is based on the resolution rule.
I understand completely. Thank you.
This is my main goal. So now I will check if you're understanding or not. So I will ask a question. Is the proof by resolution the only way to achieve the goal to make the agent perform such intelligent inference in general? Is it the only way?
I would say no.
Yeah. So this is the most famous. This is the most well-known. This is what we are going to see. Doesn't mean that there are other ways to perform this. This is one of the ways. It is the most common. This is why we're going to check. Okay, so can you explain for me what does it mean to derive contradiction from a given set of clauses? Contradiction, it's like I'm confused. You are Arshida, and I'm saying you are not Arshida. So a contradiction means who are you? It's better to call someone else. Is that clear? It's like in the real world. If I have, for example, not something and something, what's that result? It's not true, it's not false. It's resulting an empty or no answer. Okay? It's all based on this logic, so you keep it in mind.
Can I take a crack at it just for fun?
Yes. So
Okay.
the contract. Yeah, you can.
So if I'm reading this right,
Mhm.
what we're trying to do is prove something by attempting to assert that it's not true and then seeing that there's a problem with our assertion being put into there. So if I was going to bring this into the real world, let's say I don't know if it's raining, but my coworker only brings an umbrella if it's raining. So I try to prove my coworker is not using an umbrella. It turns out that's false. They are using an umbrella, therefore it's raining, or something like that.
It's exactly that. I'm really proud of your journal.
Okay.
You will also have extra points again. Does
That
make
helped
me
me. Thank you.
okay?
Sure thing.
So are you understanding what he's saying? That's really great.
Yeah, now I
So-
get it.
What's it?
Sorry, I just said now I get it.
Good. Okay. So what we have now, we are introducing previously the word clause. We need to deal what is a clause. It's a disjunction of literals. When we say literals, it's P, Q, R. This is a literal. When we talk about disjunction, it's the or. So if I have something like this, for example, it's a clause. Okay. Now what we will do, we'll be talking about the conjunctive normal form, which is very famous. But before talking about that, I wanted to make it simple in your brain. Next, we will see it in the next slide. So when I would say conjunctive normal form, it's nothing than a logical sentence that is a conjunction of clauses. Means I am going to have, for example, my sentence, which is representing like this. It is going to represent different like boxes, I would say, that are having in between, or these boxes are connected via and. This and this and this. If I dive into each this, there is a set of possibilities, this or this or this or this, okay? So this is a clause. Do you see any by conditional, then any implies, anything? No. So you only having or, which is inside the parentheses. You are having and, just connecting them, okay? Keep it in mind. Now you will be familiar with the conjunctive normal form. So in order to solve this proof by resolution, the very first step is to achieve this conjunctive normal form. I'm sorry for interrupting you, but last time I was saying that make me remember to take 5 minutes. Pause. So excuse me, if you are not remembering me, it's not my mistake. Okay? So I will finish this and we'll take some rest, at least. So what we have now, first step to achieve the proof by resolution. First, we will achieve this conjunctive normal form, CNF. So how to achieve this? The first example here, is this a CNF?
No.
If you
No.
see something then, boxes in parentheses, between them there is an or connected with an and, you are not in the CNF form. So this is not the CNF form. The CNF form is rather something where I see boxes, parentheses, with or, I can find them connected with and. Is that clear? So moving now from this step to this step, how can we do that? It's thanks to that table I'm saying take notes of, okay? So if I have, for example, A implies, I will take the simple example, A implies B. B bidirection means A implies B and B implies A. D implies F only, now we will focus with one to just remove the imply. D implies F means not F.
Yeah.
Huh? No, yeah, extra points.
Or
Or and. Check it.
or
Or I'm going to give you extra
Well,
points.
negative F would equal negative D.
No, we are not in the negation. We are just removing the imply. A implies B, negative B,
or
or A. Okay? Believe me, I will double check. Okay, where we have seen that so far? This famous slide. This one?
no.
No. This one, sorry. So where is the implied? This one. A implies B. It's equivalent to, I will come back to in the other direction, not B.
Or
I think the one.
Oh, yeah, sorry. Or,
yeah, so I'm
so we don't come back with the wrong direction. We keep moving. It's a not P, just we replace this like a row, imply with the or. So not P or Q are Farah also is having extra points. Okay. Is that clear, please? Why I'm coming back to this slide?
Yeah, that makes sense.
While revising, you must come back to this slide. This is one. Okay. No. Where are we? There we go.
Is that like something we should memorize or?
It's the logic that we are based on, that you by yourself, you were saying in the start. So you know that. Be sure that you know that. Okay? So what we have now, we are sure that we are able now to move from this like typical with like biconditional to somewhere where only we have boxes that are connected via these ands. Boxes connected via these ands. Inside the boxes, we only have, or there could be negations as well. It's not a problem. Once this is done, I have my like sentence written in the conjunctive normal form. By the way, the conjunctive normal form, I cannot give you a sentence and you say to me, I cannot write it in the conjunctive normal form. Any sentence that I can give where you find imply or the by condition, you must write it in the conjunctive like normal form. It's a good idea for the exam as well. So the second thing now, once I have it's all set, I have this CNF. I need to apply resolution inference rule to cancel out complementary literals. This is the contradictions that Jeremy was explaining. When I have something and not that thing, it cannot happen. So if I have not B and B, I would consider that as complementary like literals, and I won't consider both of them because it's not something which is sure or makes sense ever. It gives empty list, which is equal to false, let's say. It's not true. Okay? Please, clear? Online.
Oh, sorry, I unmuted at the wrong time. Yeah, that makes sense.
Okay, great. So before moving to this conversion, I may give you 5 minutes rest. Or is done?
Might as well just push for
5
Yep.
days.
It's pretty close.
Okay, so please, if you again feel that I'm not giving you, it's your right, but it's maybe my mistake that I enjoy teaching you, so I forget that you guys maybe get tired. So just say to me, okay, we need rest, we are hungry, we can bring some food for the online ones, and that's it. So any questions like for the online?
Nope.
All okay?
Nope.
Okay. In person, all okay? Okay, see you next week.
All right.